Hello, everybody. My name is Dylan Smith at Structural Design and Analysis, and I'll be talking about how to use Fibersim with Parasolid part data for composite manufacturing. So I'd like to give a quick overview of our company here at Structural Design and Analysis. On the SDA side, we're about 21 and growing engineers. We have a variety of backgrounds, mostly focused on the aerospace and mechanical fields. We have two teams, a design and analysis team. The analysis team optimizes structural design via hand calcs as well as Femap and Nastran. Our design team provides design services for all sorts of vehicles in all sorts of steps of the design cycle. So just to give you an overview of some of the projects that we've been working on recently, runs the gamut from small UAVs to prototype aircraft as well as certified aircraft, and then up into space vehicles and launch vehicles as well. So we have a wide range of experience in the industry here, and a lot of diversity in the projects that we've come across over the years. We're also a Siemens Value-Added Reseller at SDAsoftware, so we sell these software packages here, Femap, Nastran, Simcenter, as well as NXCAD and Fibersim, which we'll be talking about today. We perform training on Femap and support on all of these products as well. If there's any support question that stumps us, we can go directly to Siemens and get the answer for you. We have a variety of webinars every couple months, so if you're interested in this one and want to learn about more, make sure you subscribe and tune into the upcoming webinars that we have in the future. So now I'd like to jump into the webinar today about how to use Fibersim in your composite design process. I'll give you a quick overview of the webinar here. So first we'll talk through some of the industry challenges that the industry faces, some benefits that Fibersim can provide to address those challenges. I'll give you an overview of the demonstration that I plan on providing. We'll jump into NX and Fibersim to perform that demonstration, and then I'll summarize some of the benefits that Fibersim provides, and then we can go over any questions if you have them at that time. So first, to jump into the industry challenges. So in the composite design process, often there are disparate systems and manual workflows which result in wasted time and money. So what this means is a lot of times you might need to manually create a ply shape, measure a tool, work with flatten out a paper onto the tool to generate your flat pattern. That's tedious and time intensive. This results in overbuilt yet under-engineered products. So what that means is that without a accurate understanding of the fiber location and placement by the designer or the analyst, you need to run with higher margins, which result in extra material that you might not otherwise need. And this results in not quite as optimized of a product as is possible. This can also result in inefficiencies getting a product to market, and potentially increased chance of failure due to the risk involved with inconsistent production quality and not fully understanding the fiber placement and fiber locations in a part. The traditional composite part development process often is interdisciplinary, but it often involves several models and masters in each discipline group. This results in repeated or redundant tasks and data, especially when changes need to happen. So manually creating 2D drawings is tedious, error prone, often doesn't add much value, and could open the door to risk of misinterpretation. Any changes that need to be made in each one of these areas needs to be duplicated across all the disciplines. For example, if a part gets updated, the tooling needs to get updated, the flat patterns, any exported laser projection data often needs to be updated. So manually creating a lot of these deliverables creates additional time on the designer and creates a manual process that's really tedious and time consuming to perform. Any changes that need to be made when they're caught late in the game can often be very difficult to implement and will extend your schedule in an undesirable way. So some of the benefits that Fibersim can provide to alleviate some of these issues, we'll talk about that now. So Fibersim solves a lot of these challenges. I'll briefly on the left here, I'll overview the process that Fibersim can provide here. So first we'll start with an OML from a loft, preferably using NX, but you can use pretty much any CAD package. Today we'll go over how to bring in an OML from SolidWorks. You author your ply definition, your composite design definition with Fibersim. You can, in the top right here, you can simulate the producibility analysis of the part here. So you can simulate how the plies are actually going to lay up in a tool and really get a window to the manufacturing floor, understand and anticipate any manufacturing challenges that might pop up down the road and address them earlier on in the process. So when you do that, you reduce the schedule impact, the cost impact from making these changes, and get to address these problems earlier on in the process. And finally, generating and sharing all required manufacturing data is a breeze with Fibersim. It really just takes a couple clicks of the button to export flat patterns, laser projection data, documentation for drawings. All of this is automated in a way that really speeds up any revisions or changes that need to be made. So this all results in rapid conceptualization of a product using automated tools and integrated systems, improve communication with the between manufacturing, design, analysis to really get everybody on the same page, improve production efficiency, and eliminate any uncertainty in terms of uncertainty of the designer and analyst understanding of what's being built, as well as uncertainty from inconsistent production quality. So these are the key value benefits that Fibersim provides. Now today I'll be talking through how to use Fibersim with SolidWorks. It's fairly trivial, honestly, to bring in a SolidWorks model. Once you bring that model in, you just follow the same Fibersim process that you would with any part. So integration with SolidWorks or any other CAD package is pretty straightforward. And all the benefits that I've talked about for Fibersim, Fibersim can deliver regardless of the origination of the models that are being made. So now I'll go over the demo that I plan on showing you today. This is a process here that we'll follow. So first we'll open a SolidWorks file in NX. There's a little bit of model prep required to get this model ready for Fibersim. So I'll get that, I'll show you how to do that. We'll generate the data in Fibersim. So the zone boundaries, the ply boundaries themselves, and then as you can see in that image, simulation of those plies in the part. I'll sort of simulate receiving a design change, a new revision to the part, and what's required to bring that in. you can do this while preserving all the work that you've done up till then. So one of the benefits here is that there's not a lot of duplicated work here. You can maintain that work and just change aspects of the part that have changed, and then update that Fibersim data to reflect that revision and get those manufacturing deliverables out the door. So now I'll jump into the demo. I split this demo up into two parts. So this part here will be authoring the product definition, the first phase of the Fibersim cycle. So we'll prepare this model for Fibersim, import that file into NX. We'll author the definition of the composite objects. So we'll specify the laminate and the rosette, overlay zones. We'll create layers and plies from these zones. We'll perform a little bit of splicing and adjustment of some ply drops, and then we'll run the producibility simulation here. So if I jump into my NX screen here, actually I don't have it over here. Okay, so we start with just open a new part here. I can open it here. You can see that in my open tab, I can specify a SolidWorks file here. So you can just open that directly, click OK, and then you can see that it brings in those bodies pretty easily. So in this part, it's a skin. It's got laminate here, two cores here, and you can see some sketches where some of the zone boundaries are created. You have a thicker region zone in the front here and a thinner in the back. So that's our part right here. And then I'll jump ahead to show you what we do to prepare this part for Fibersim. So in this file here, I have that prepared. You can see the model tree here. It's not too much involved, really. We just need to extend the OML surface to the manufacturing extent. So right here, this boundary here is the net boundary that we'll trim to, but when we're laying this up, we'll obviously want to lay up a little bit more and then cure the part and then trim it back to our final boundary. So that's what I did here. You have your origin and zero direction point that establishes where the plies are starting from and which orientation they'll be laid up in. And then I do have a curve here on this surface. This specifies that zone region that we'll show later on. So that's pretty much all that's involved here. And then at this point, we can jump into Fibersim. One last note, though, that I wanted to show is often it's important to use clean geometry, clean surfaces. You can examine your geometry and just make sure that there aren't any, let's say, like divisions in the surface, any gaps that are hiding. So you can use this to point that out for you. So here it highlights the edges of the part here. If there are any internal edges or gaps, it would point those out for me. So it looks like I don't have any issues here. So that's a useful tool to just make sure that there aren't going to be any issues that pop up later down the road. So I have Fibersim open here. I just opened that. And I'll walk you through just the brief overview of Fibersim. So it's a pop-up. Really, the core navigation is done in this application tab. So we have design split up into three categories: design, manufacturing, and the specification tab here. So in design, and I'll walk you through chronologically how you set this up, but it's pretty much just in the laminate tab, you're pointing out the laminate, you're pointing out the OML surface. The rosette, you point out the origin and 0 degree vector here. And then next I'll jump into the creation of the zones. So in this part, I have 2 zones. This is how you sort of describe the part. I have 2 all over plies and then 2 pad-up plies in the front region here. So that's defined by these overlay zones. And this provides a high-level definition of the part. And you can see in these 3 steps, I have the part pretty well defined already, and really just setting this up is just a couple clicks. So not really that hard to get to where I am so far. At this point, you perform a zone to layer. So these are 2 plies on each, right? So I want to sort of describe the part in individual layers. So that's what I'll do here. So based on these zones, I create an offset specification, which is pretty much just the ply drop rules that I want to associate with this zone here. And then I split this off into 4 layers here. So one all over, and then one pad up, and then one pad up there. You can see the orientation is shown here. Then I also have my material. So let me jump into that material here. The material cards are listed in this pop-up here. You can associate whatever material you need. Fibersim comes with a database here that defines a library of materials, including their the roll widths, the material thicknesses and densities. So if you have your own materials, you can import them into this library and then simply associate them with each individual zone that you're creating here. So pretty easy to go and do that. So now I have my layers here. One thing I'll note is, as you can see that that laminate or that ply drop offset spec is driving the offsets between these ply drops here. I have it a little close to the core edge here. So if I want to change that, I can go into here and adjust that. So here I can adjust the ply drop distance. So if I want to change that to 1/2 inch, I can. But if I want to offset these, I can also do that, which I just did. So now you can see that with just typing in one value, I can move these ply drop boundary off of that core and adjust it without having to change the geometry or the curves too much. So next up, we have our layers here, but you know, that only describes certain portion of the part. For instance, if you have splices between, you know, if you have a really large part and you need to splice a part, then you need to split that up into individual plies. If you have a dart that needs to be added to the part, that will all be performed in the ply tab here. So what I'll do here is generate plies from these layers. And you can see I have my plies over here. So 4 layers go into 4 plies initially. But you can see that when I run the simulation analysis here, I get a pop-up saying that my material width is exceeded. So based on the material width that this material card had, the roll width looks like I need to add a splice in order to improve that. So I'll go and modify this. You can see that it's flagging that I exceeded my width. So I can go in and type different values here to sort of move a splice line where I want it and sort of adjust that to get that where I need. So you can see I move the splice line around the center of the part here. I can generate that. And then you can see that that curve is automatically created. I don't have to mess around with planes or anything. It's a tool integrated in Fibersim that lets me generate that curve pretty quickly and easily. So with this, all I need to do is associate that. I have my offset specification here. I associate that to my splice group that I'm using. Okay, so this splice group here, you can see it in a similar way that I drove the specifications of the ply drops between the zones. I can drive the specifications of the splice group here, create a rule, and then have Fibersim follow that rule and implement that in the rest of the part here. So that's what I have here. And then I can go ahead and, let's see, on these two plies here, I want to splice them. And then once I do that, you can see I have these plies split up in two. So I have a left and a right spliced in the middle here, and you can see it that they're offset as per the specifications that I put forward. So if I want to simulate this, you can see that now I don't have that flag, that error of net width exceeded here. So now I'm good to go and continue with authoring the definition here. So you can see this part has core, so to integrate that, I'll jump forward a little bit to this this file here, which has that core implemented. You can see that the core I have called out here, it's pretty simple to call out a core. You just point out the solid body that you're referencing, or you can define a core region with curves in the same way that you define the zone. So cores are in, and then you can see I have a couple over core plies here that are created. Okay. Yeah, I think here you can show simulated plies over the core here, so it actually takes that core into account when it's performing that simulation. So it's a very powerful simulation tool to accurately represent the curvature of how the plies go down in the curvature of the part there. So at this point, we have this part pretty far along. Okay, I'll jump back into the PowerPoint right now, just to give us a little break from the demo there, and we'll just overview what we went over. So Fibersim here, it enables authoring a concise definition of the composite part design. It really leans on automated tools to create those layer and ply boundaries, as well as splicing boundaries. So those automated tools really reduce that those tedious tasks of, in a drawing specifying all the ply drops and everything. It's able to really speed a lot of that up. It alleviates any errors that are associated with that, eliminates a lot of those non-value added tasks. And most important though, it identifies any manufacturing issues earlier on in the process. So you're able to identify those challenges, correct for them earlier on in the process so that you're not doing it in a costly way on the shop floor, really bringing the designer to the shop floor earlier on in the process, giving you a window to the shop floor, and really tightening the loop on between manufacturing and design here. So I'll jump back into the demo now. At this point, we have our part pretty much well defined, but I'm going to show us a part revision. So we'll import some changes to this part. We can update this Fibersim data while preserving that previously completed work. And then I'll jump into the generation of the flat pattern deliverables and IML surface offsets. So we're at this point. I'll jump in here. So to import this change here, it's pretty simple. You just go File, Import, and then you bring in these bodies. That's what I have listed here, I believe. So we have, let's see, the core regions have shifted. You could see a rib, maybe a rib needed to change, so that got shifted over. And then you can see here we have a cutout for a pad up region in the back here. So this is a pretty typical change that might need to be made. And we're going to try to incorporate this into our Fibersim part without losing too much work here. So if I go into If I go into this this model here, which has been prepared, I can show you what's involved. So first of all, the main difference is the core, right? So I kind of showed you this earlier, but in the core here, all you're doing really is just specifying the solid. So you can, especially when you're importing parts here, you just reassociate it with a new solid, and then it's pretty much ready to go. So not a lot of work required to fix this up. It's just a couple clicks and you're off to the races there. The next thing though is pretty much just a creation of a new zone, which is pretty trivial to do in Fibersim. So I have all my zones, overlay zones highlighted here. And just to go over them again, so I have all over zones under the core. I have all over zone over the core, so 2 plies each. I have 2 plies up in the front here, and then the design change that was made was to add 2 plies to the back here. So Fibersim makes it pretty easy to pretty much just copy paste. You can see, especially with this one, I can just copy and paste that over. If I look at my aft pad up here, all I really need to do to define this zone is an origin point, which I could just specify at the center here, a boundary. So these boundary curves, as long as you just project a sketch onto the surface there, you got your boundary. And then your laminate spec, which I have over here. And it's pretty much just defining 2 plies for this aft pad up region. So that's all pretty easy to do. So now I have all my zones created there. Let me see if there's anything else that we need to do. Not really too much. So you can see in the ply tab here, all you need to do is really just regenerate a lot of these plies. The splice group doesn't really get affected because that's all driven by the all over plies, which weren't really changed too much. So you can see here, this is our final list of plies here. So we have those splice plies all over under the core. You have these pad up plies here. Once again, this is driven by that ply drop specification that we use. We just use the same specification as up here. And then some over core all over plies. So at this point, we're sort of ready to get this part manufactured and out the door. There's a lot of functionality of Fibersim. I don't have the time in this demo to go over it, but you can create, you can create design stations to sort of look at a specific point and understand the ply schedule and orientation at those points. You can do cross sections and basically generate the cross section to visually represent the part here. You can go and get an accurate weight estimate of the part here. So in the analysis tab here, you can see I have part estimate weight listed here as well as the CG. So this is good for not just keeping your weight balance updated throughout a program, instead of waiting until this part gets made and trimmed, you have a very good estimate here that takes into account all the ply drops and all the precise locations. I mean, this takes into account the area, calculated area of each individual ply that you'll be cutting and sending to the Gerber machine. So this is as accurate as you can get right here. So really powerful tool here to get those weight tracking efforts as up to date as possible. And also for material usage, you can quickly, as long as you split up a ply into the zones or split up a part into the zones that it needs, you can get a good understanding of how much area, material area you'll need, which is down here. In terms of other deliverables to generate, there's the flat pattern generation. So let's see if I go to one of these here, you generate that reducibility, then you spit out that flat pattern, and I have all the flat patterns sort of spit out here, but it'll generate that in real time, just the click of a button here. So you can see all the flat patterns for the part are shown in the right here. And with that, it's just a quick couple clicks to export that to DXF, get it out the door. These can be associated to a drawing in NX and pretty much just automatically update the flat patterns in a page of the drawing and show that location on the 3D part. So really automating the drawing creation process, which is great. There's laser projection, exporting. That's once again just the click of a button. So there's a lot of manufacturing deliverables that are really quick and easy to generate here. Finally, I'll show you the basically the final solid part here. So Fibersim's able to simulate the IML surface of the part, which we have here, and I have that thickened into a solid body here. So this is useful if you're interfacing with other parts. Obviously, you need an accurate representation of that IML. So Fibersim takes into account the ply drop distances to create this and gives you as accurate of a representation of that IML as possible. Okay, so I'll jump back into the PowerPoint here to conclude. So after that second part of the demo here, just to recap, we're able to accommodate part revision changes and make them pretty easily without duplicating work. All of the definition of the part that it done previously is preserved. There's really all that we needed to do was reassociate a couple cores that changed and then create a new zone boundary there. So it was pretty painless to do that. We saw that Fibersim has a suite of tools to give the designer information at their fingertips. We just scratched the surface there, but quick and precise part weight estimate. Once again, those cross-section tools are pretty powerful as well. And then the generation of accurate flat patterns, which are associative with the 3D ply definition, update in real time. So, and exporting them, which is a breeze. So that's sort of the tail end here of the deliverable generation part of the process here. And once again, that is automated in a way that saves a lot of designer time and makes that process a lot more painless. So just to summarize some of the benefits that Fibersim provides and conclude the demo, we have here a much faster process for defining the laminate. Since these tools are automated, we can, as a designer, I can very quickly and easily set up zones, set up ply drop rules to automate the process of creating those individual plies, as well as splice rules. So setting up the rules and letting the computer do all the work really speeds up the process of defining a part. The feedback that Fibersim provides to provide you producibility analysis is really helpful because it simulates how the ply is going to lay up into a part. So instead of waiting until something gets made and hoping, crossing your fingers that it's going to lay up correctly, you can anticipate that earlier on in the process, plan for it, and really reduce any costly late in the game changes that might need to be made, increasing the certainty that you have going into the manufacturing process of being able to make a part on time. It reduces, Fibersim allows for a reduction in design effort to make changes to design. because of the fact that you're eliminating a lot of the manual variables, the manual tasks from the effort and keeping it in the computer. So Fibersim and the model that Fibersim has is a digital twin to the actual part being made. So it reflects accurately the part being made, and it's you make your changes in one place, and then those changes are propagated downstream. Reduces cost due to scrapping. So this is due to a number of factors, but number one, fewer NCs and issues on the floor due to a more consistent production quality from Fibersim will reduce scrap rates. Since you're able to accurately simulate the ply shapes, you can cut those plies a little tighter on the machine and save on material as well. And then you can finally increase production rate with a automated process here. So instead of relying on manual expertise and individual laminate technicians to make decisions, you can make those decisions from a programmatic standpoint and create very repeatable ply shapes and create designs that are much more consistent from part to part, since doesn't rely on the fly, on the shop floor decisions to be made. So this all results in savings of bringing the production of a proof of concept down to days instead of weeks or months for a given part, increasing the speed of developing flap patterns, drawings, and documentation due to Fibersim's automated tools, achieving higher part-to-part consistency by reducing that reliance on manual expertise and allowing the simulation capabilities of the computer and the automation capabilities of the computer to document a parts definition. And to another big benefit of Fibersim is to reduce the ambiguity and risk due to lack of full understanding of material use and fiber orientation. So by closing the gap between manufacturing and the design and the analysis side, you're able to get everybody on the same page when it comes to parts manufacturing and improve structural performance and achieve lighter weight designs by knowing exactly what your part's going to do, exactly where your fibers are going to be laid up. With that, that concludes the demonstration here. We can go over any questions that you all might have, but just to summarize, my name is Dylan Smith. There's my contact information there. And if you have any sales questions, you can reach out to Dennis Carter, who's listed there as well. And look forward to seeing you at the next demo. So SDA providing mentoring to companies to assist with manufacturing composite parts. We certainly do that. We offer a wide range of services with regard to composite manufacturing. So we can certainly help with that, whether it comes to assisting the customer on Fibersim. So either purchase a Fibersim package or use our services to help you out with a certain aspect of a certain program. We can certainly talk to you about setting up Fibersim software bundles that can get you started with new projects. There's a wide range of bundle options to choose from. Okay, if there aren't any other questions, that'll conclude the demo here. Thank you all for joining.